Alright, so this is my second video for you guys, this time working the electric field and potential, which says electric field and electric potential calculations. Remember, electric field is technically electric field intensity, shown with an uppercase E and measured in newtons per coulomb. Electric potential, also called potential difference, is uppercase V, sometimes called voltage, and it's measured in volts, which is also an uppercase V. The equations, there's four of them. Electric field intensity equals force over charge. Voltage equals field intensity times distance. Voltage equals work over charge. And then we may need the fact that work equals force times distance, which is a first semester equation making a reappearance. I have a better calculator today and installed a calculator app, so hopefully I will embarrass myself less with all of these exponents. This is why it's so important to be careful. Alright, let's dive right in since we have 10 problems to work this time. A positive charge of 1.7 times 10 to the negative fifth coulombs experiences a force of 2.28 newtons when located at a certain point in an electric field. What is the electric field's intensity at that point? So, 2 is 1.7 times 10 to the negative fifth. Force is 0.28. And we are looking for uppercase E. So based on what we've been given, we're going to use this equation, E equals F over Q. So, E equals 0.28 divided by 1.7 times 10 to the negative fifth. If you know anything about exponents, you should know we should get a large number for our answer because we are dividing by a negative exponent. So that's 0.28 divided by 1.7 e negative 5. And I'm getting 16,470 newtons per coulomb. This is running, this is in newtons, and this is in coulomb. That can also be rewritten as 1.6 times 10 to the fourth newtons per coulomb. Alright, number 2. How strong will an electric field have to be if a positive charge of 7.4 times 10 to the third coulombs experiences a force of 5.6 times 10 to the negative 2 newtons when it is placed in the electric field? So, it's worded differently, but it's basically the same problem. Our charge is 7.4 times 10 to the negative third. It experiences a force of 5.6 times 10 to the negative second. So again, E equals F over Q. E equals 5.6 times 10 to the negative second over 7.4 times 10 to the negative third. These are mathematically simpler because you're just dividing one number by another, but you are dividing exponents, so it is maybe even more important than the problems I worked before that you are making sure you're entering those exponents correctly. I really cannot stress enough what a big difference that's going to make. So, I'm getting the E equals 7.57 coulomb. Number 3, the electric field intensity between two charged plates is 1.5 times 10 to the third. So this one's set up a little bit different. They're giving us E, 1.5 times 10 to the third. The plates are a distance of 0.08 meters apart, 8 centimeters. What is the potential difference in volts between the plates? So we are looking for potential difference or voltage this time. We have field intensity and distance. So we're going to go to this equation. D equals ED. Students usually make jokes about this being V equals erectile dysfunction. As I've said before, whatever helps you remember the equation. So 1.5 times 10 to the third times 0.08. They're doing some kind of construction out in the hallway of the hotel I'm in, so hopefully that's not too distracting on the video. My apologies. I'm getting an answer of 120 volts. Alright, a voltmeter indicates that the difference in potential, which is just another way of saying potential difference, between two plates is 55 volts. The plates are 0.022 meters apart. What electric field intensity exists between them? So we have the same variables, so we're going to use that same equation, E equals ED, but now it's E that we're searching for. So we have 55 equals E times 0.022. So we'll divide both sides by 0.022. 55 divided by 0.022. And I'm getting equals 2,500 newtons per coulomb, which is the same as 2.5 times 10 to the third newtons per coulomb. What work is done when 47 coulombs of charge? Man, that is a ton of charge. I just want that on the record. What work is done when 47 coulombs of charge is raised in potential by 5.3 volts? So this is for you, it's a little funny, but raised in potential, that's saying potential difference. So that's U, and we are looking for work. So we have QVW, we're going to use this equation. U equals W over Q. So 5.3 equals W over 47. So we're going to cross multiply. W equals 5.3 times 47. And you actually get 249.1, but apparently the overload is two nice round numbers, so sure. We'll say that that's 250. Remember that work is equal to the change in energy, so they have the same units as energy, which is joules. Alright, number 6. If 280 joules of work are done to move 3 coulombs of charge from a positive plate to a negative plate, what voltage difference exists between the plates? So now we're going to determine the equation as before, except we don't even have to do anything equation. So we just do 2 divided by 3. I'm sure if I was a better mathematician, I would be able to do that in my head. But I'm not a mathematician. So we get 93.33 volts. Let's go ahead and scoot this way up. A 6-volt battery does 4,500 joules of work. That's a lot of work. That means we are going to probably, well, hold on. So a 6-volt battery, so potential difference is 6, does 4,500 joules of work by transferring charge. How much charge is transferred? Well, this is a ton of work being done by a relatively small amount of voltage. So I'm going to go with it needs to be a lot of charge. Let's see how it works. So V equals W over 2, 6 equals 4,500 divided by 2. If we cross multiply here, we're going to get that 2 is equal to 4,500 divided by 6. Which comes out to 750 kilowatts of charge, which is in fact a lot of charge. Alright, number 8. A force of 0.59 newtons is required to move a charge of 4.3 times 10 to the -7 kilowatts in an electric field between 2 points, which are 0.263 volts. What is the potential difference or voltage between the 2 points? So we have F and Q. Now, this is interesting because we're looking for voltage. We have F, Q, and D. If you look back up here, there is no equation that has all of this in it together. I believe I actually gave you guys the equation that has all of these in it together. But it comes, and you guys can't see where I'm pointing, sorry. So there's no equation up here that has F, Q, and D, and V, all in the same equation. I think I gave it to you guys. It actually comes from substituting these two together. So if you know that work is force times distance, you can do force times distance over Q is equal to V. Although that doesn't sound familiar. Hold on before I embarrass myself. Alright, so the equation that I was actually thinking of is a different one, and it is not usable here for reasons that I don't really want to get into on this video. It's not important to the test. So we are going to combine those two equations that I was just pointing out. Instead of combining them up there in equation form, what I'm going to do is combine them down here, which is kind of the way we've been doing things. So we need voltage. Considering that we have charge, the only equation for voltage that includes charge is voltage equals work over charge, but we don't have work, so that's what we're going to need to solve for first. Work equals force times distance. So 0.59 times 2 Wake up phone, you need to be a calculator. 0.26 times point. Come on, phone. 0.26 times 0.59 is giving you 0.15 joules. Now we can use the equation for the molecular charge. So E equals 0.15 divided by 4.4 times 10 to the negative 7. And it's still a pretty large number because I am dividing by a very small number. Again, that's a really good skill as an honors level student to have, to kind of gauge how big your answer should be. And I did account for my large number. I did not get exactly the same thing as the answer key, which is probably because how I wanted on this step. Because I got 3.48 times 10 to the fifth. As you guys know, I would accept either of those answers. 3.48, 3.5, 3.6. It's just rounding differences. Alright. Only 2 more to go. These are going a lot faster than the Coulomb's law problems because there's less large numbers having to be dealt with at a time, which we like highlight. A rubber rod is charged to 3,200 volts. And the amount of charge on the rod is 8.2 times 10 to the negative 6 coulombs. And the potential energy, what is the potential energy? Ooh, okay, so this one's kind of interesting because it asks us for potential energy. If you go and look at our equations at the top, there are no equations up here for energy. That uppercase E is electric field intensity. Don't confuse that for energy. And there's particularly not any that say potential energy, which would be PE. So, what you have to remember is that work done is equal to change in energy. And this is a change in energy because the rubber rod was charged by friction, which is what we did in lab. So we gained that energy. So it is a change in energy. So they're asking us for potential energy, but what we can solve for is work. So we're looking for work. We have V, we have Q. So V equals W over Q. So we do 3,200 equals W over 8.4 times 10 to the 6th. Multiply. So work done is going to be those two numbers times each other. 3,200 times 8.4 times 10 to the negative 6. This should be a pretty small number because while this is relatively large, this seems real small, and we are multiplying. And I am doing that the work done is 0.027 joules, which is about what I expected, so good. One more. Alright. How far is a 9.1 times 10 to the 5th charge? 10 to the 5th. Oh, negative 5th. That makes more sense. Alright, that's not readable. Let's start over. Okay, 9.1 times 10 to the negative fifth charge moved in an electric field if the voltage over the distance is 5700 volts and the force required is 0.46 meters. And we are looking for distance. Alright, this is another one that's going to be in 2 steps to get what we want, because we're looking for distance and we're talking about and there's actually 2 different ways you could get to this. Let's look at that. If you look up here, so what we want is distance, which means we need to be using either, you can't see what I'm talking about, we're looking for distance. So the only 2 equations that use distance are d equals ed and work equals fd. If you look at what we don't have work and we don't have electric field intensity. We don't have W or E. So we're going to have to find one of those 2 before we can actually solve for distance. And we can actually do either one. We have F and Q, so we could solve for, we couldn't do either one. I am made of Y's. Let's go back and look at Y. Because we need to find either electric field intensity or voltage before we can find distance. If we wanted to find voltage, we need W here. We don't have W, that's the problem. So we can't find voltage. So we're going to have to instead find electric field intensity. So, electric field intensity is equal to force divided by charge. So for us, that is 0.46 divided by 9.1 times 10 to the negative fifth. 0.46 divided by 9.1 I'm going to get in 5,055, which you could write as 5.1 times 10 to the third. Whatever. No change in answer slightly depending on how it's around. Now that we have this, we can say that we're looking for distance. So 5,700 equals 5,055 times D. These numbers are pretty close together, so D should be pretty close to 1. So 1 to divide this, it should be higher than 1. Because we're dividing both sides by the small, it should be bigger. So 5,700 divided by 5,055. And D equals 1.1 meters. Yay! Those are pretty far apart. Alright, that's the end of this math.